so just to reassure you, they're still rejecting my papers. They're now rejecting them because they're not about deep convolutional neural nets. But, so in fact, what I'm going to talk about today is a rejected NIPS paper. Okay. So physicists will tell you that 95% of the stuff in the universe is not what they were paying attention to. It's something else. And the point of the title is that I want to show you that 95% of what a neural net learns is not what you were trying to get it to learn, and is not what you tested on. It's something else. That explains the title. So the easiest way to extract a lot of knowledge from a big data set is to train lots and lots of different models. And different models will notice different things, and the more different you make the models, the better. Even if they're all neural nets, you should make them as different as possible. And in fact, if you can train lots of models, it's helpful if the individual models overfit. Because when you average them all together, that overfitting you get rid of again. So what we do at test time is we average all these models together. We average their predictions. There's a couple of ways of doing that. And that's how you win a machine learning competition. You have lots and lots of different models. If your rivals are doing something, you be sure to include a bit of what they're doing. And you average it all together, and you hope you get a better average than other people. There's just one problem with that. If you're someone like Google, and people are talking to Android phones, every time you run the acoustic model, which is sort of every 10 milliseconds or so, you don't want to be running hundreds of different models. It's just too expensive. And if you think of a big ensemble, it's very redundant. There's not much knowledge per parameter. It may get more knowledge than building one model, but not much per parameter. And so it's no good at having a small footprint in memory and being fast to compute it. So we've got a contention there. And I want to give you an analogy of other systems that have solved this kind of problem. So insects have this problem. Insects have to get lots of energy and nutrients from the environment. And for that, you need to sort of have a big mouth and do nothing but eat. They also need to fly around and mate. And for that, you need to be light and agile. And these two are completely incompatible. And so insects solve this by having two totally different forms. What they do is they have a larval form, not all of them, but most of them. They have a larval form that's optimized for eating. It just sucks stuff out of the environment. And then what happens to the larva is it gets turned into soup, and out of this soup you build an adult, which is basically a different organism, just built out of the soup. If you think about real mining, where you want to get gold out of the earth, you don't burrow down into the earth looking for little pieces of gold. What you do is you find a place where there's quite a lot of gold, and you scoop up a big pile of pay dirt, and then after you've got the stuff, in a small enough pile so you can put it in some great big smelter, you now do something else to get the gold out. But you first get your hands on it, but not in the right form, and then you refine it. And we should be doing the same in machine learning. We've got these huge data sets. We want to get the knowledge out of the data, but maybe we can get it out in some clumsy form, and a big ensemble of models is a clumsy form. But once we've got it into that form, maybe we can now squidge it into some little model. So the main idea is that if you learn a big ensemble of models, or even if you just learn a very big model with lots of regularization, after you've learned, you've got your hands on a function that maps your inputs to outputs. And so you've got your hands on more than just the training set. Forget about all the parameters in the model. Just think about this function. So we've got this big ensemble of models. We're going to average their predictions, and that average determines the output of a function that takes an input and tells us the probabilities of all the different classes, let's say. And what we're going to try and do is get that function into a much smaller model. So we're going to have this two-stage process of first get the function and then get it in a small model. I thought I'd invented this idea, but unfortunately, Caruana and his collaborators published a very nice paper on it in 2006. It's basically the same idea. They had a slightly different way of getting the knowledge out of the ensemble into the small model. And this paper was widely ignored. I'm surprised it wasn't rejected, because it's such a good paper. I think it's got 39 citations, and I assume that if there's a good paper out there, people will tell me about it, so I don't actually need to read the literature. And in this case, that was a big mistake. People didn't tell me about this till I started giving talks about the same thing. So here's the way we transfer knowledge from a big ensemble to a little model. And what I'm talking about today is mainly when you're doing multi-way classification. So you've got the output of a big neural net, and it's a big n-way softmax for n classes. And when you train it, the targets are ones and zeros. And so if you ask how much constraint does a training case put on the parameters of your neural net, on average, it's at most log n bits. Even if the class is all equiprobable, it will be log n bits. Now, after we've trained an ensemble, we can, for example, take all the models in the ensemble and average their logits together, and then we can make an average prediction. That's a sort of geometric average prediction from the ensemble. And instead of making that prediction the way we normally do with a softmax, we can use a high temperature softmax. That is, the normal softmax looks like this. The probability of class I is just e to the logit going into class I divided by the sum of all the logits. But we're going to put a temperature in there that's going to be bigger than 1. And that's going to make this be a very soft distribution. And if you output a very soft distribution, you reveal much, much more information about the function, about what you believe. So I like the analogy of you're trying to learn to identify different painters. You could have a teacher who just says, that's a Matisse, that's a Kandinsky, that's a Rubens. And that would help. But it'd be much better if the teacher said things like, that's a Rubens, but it's a very odd Rubens because you might almost mistake it for a Titian. That would be enormously helpful information in learning about painters. And in fact, on these intelligence tests, they ought to ask people to give the second best answer. That would reveal much more about what people understand. It's easy to figure out what the best answer is, but telling you the second best answer tells a lot about what you believe. Okay. So we're going to use a high temperature. That's going to give us soft outputs, and it's going to turn out that's going to make it very easy to transfer the function to a smaller model. Just as an aside, if you have a whole bunch of models and you want to average their predictions, there's two ways to do it. There's the mixture way, where you just take the class probabilities output by model A, the class probability output by model B. If they have equal weights in the mixture, you say the probability of the class is the average. And then we can do the same, but taking a geometric mean. If we take a geometric mean, these numbers don't add up to 1, but I'll still call it a geometric mean. We'll just assume we're going to normalize them so they do add up to 1. And if you take a bunch of models with softmax outputs, and you average the logits going into the outputs from all these different models, you're taking a geometric mean, because you're averaging in the log domain, because those logits go inside the exponential. Okay, so these are the averages I'm going to be talking about mainly, but what I say works for these kinds of averages. Okay, so here's an example of, let's suppose these are the target outputs for something that's recognizing objects and images, and the training data says this is a dog. Once you've trained up your big ensemble of models and you average them, your ensemble says probability 0.9 is a dog, probability 0.1 is a cat, probability 10 to the minus 6 is a cow, and probability 10 to the minus 9 is a car. Now, as far as any cross-entropy cost function is concerned, things with very small probabilities for the target values are irrelevant, because that small probability comes outside a log, and so if you're trying to match this, this might as well have been 0, and this might as well have been 0. And that's what I call dark knowledge. If you think about a display of this where 1 is white and 0 is black, then these will be black, right? If you display this graphically, you won't see anything here, you won't see anything there. And one thing you won't see in particular is that cow is 1,000 times more likely than car. That's where almost all the knowledge is. That's the dark knowledge. When you've learned a classifier, almost everything it knows is about the relative probabilities of things that it's almost certain are wrong. There's a huge amount of information there. Okay. And the question is, how do we make use of this information in order to transfer this function to another model? And the first thing we need to do is make the information not be so dark. And so we take our softmax, we raise the temperature, and if you raise the temperature of the softmax, now what you'll get is that dog will still, the most likely will still be the most likely, things that were only an order of magnitude less likely will be almost as likely now. And this will now have some noticeable probability. And there'll be a lot of these, right? A lot of different things like that. And so the target values you have will now convey much, much more information than target values like this. It's a much richer kind of label. If you just train on soft targets, you can transfer knowledge from a big ensemble to a small model quite efficiently. It actually works better if you also include the true targets. When you include the true targets, you need to give them a smaller weight, and that's because the gradients you get for soft targets are smaller, because the soft targets are much softer. And provided you give a much smaller weight to the true targets, it's a big help to include them as well. So the way we actually train these models, I call this distillation, because we get the stuff, we refine the knowledge by using high temperature, is, suppose we're training a neural net now. We have the soft targets that we got from some big ensemble. And as we're training our new neural net, our small distilled model, we use a high temperature in its softmax too, to try and make its probabilities match the soft targets. We use the same high temperature that we used to get those soft targets. But with the very same model and the very same logits, so you don't have to compute them again, we also try and make them match the hard targets at a temperature of 1. So that would be normal training. Normal training of this small model would just be doing that. And the kind of pure transfer training that Rich Caruana typically uses would just be doing something a bit like this, and he doesn't use a temperature. We're going to use a combination. And so the trick here is, for the very same model, you're using two different temperatures in its softmax, one for getting to match hard targets, one for getting to match soft targets. And that's what seemed to work best. That's what gave us some nice results. I already just said all that. Before I show you results, I want to talk a bit about training a big ensemble of models. It's a beautiful problem to parallelize because you can just train them all on different machines and they don't need to talk to each other. It's as good as it gets for parallelization. But you might still not want to use up a lot of cores where you're doing preliminary experiments. Or you might be trying to do research on your Mac Air instead of on Google's Google Data Center. And the question is, can you train big ensembles in a more efficient way than just training them all separately in parallel? And you can. There's a technique called dropout that I introduced a few years ago, which you can think of as an efficient way to train a big ensemble, but you're using weight sharing in the ensemble. So many of you will know about this, but the idea is, suppose we have a neural net with some pixels, some class labels, and one hidden layer. What you're going to do each time you present an image is you're going to remove half the hidden units at random. Or rather, each hidden unit will be removed with probability 0.5, independently. And when you see that example again, it'll be a different bunch of hidden units that are removed. And since we're sampling from 2 to the h different architectures, where h is the number of hidden units, almost all those architectures won't get even a single training example. And the few architectures that do get an example will almost certainly only get one example. But because they all share weights, you can train this thing very nicely. And this weight sharing you could think of as a way of regularizing these models so they can learn even with only one training example. That's because they're sharing weights with all these other models. And it's a much better regularizer than L1 or L2 because it's pulling you not towards 0, it's pulling you towards the weights that some other model would like to have. And at test time, we can now average all these models very efficiently. What we do is we simply take this model, we use all of the units, but we halve the outgoing weights. And so the expected effect of the unit is the same at test time, because it's now there every time, but with only half the weight. And it turns out that if you do that, you can show that that's exactly computing the geometric mean of all these 2 to the h models. If you ran all 2 to the h models and computed the geometric mean, you get the same as just halving these weights. So this is a nice way of training a great big ensemble, and it's also a very nice way of getting the predictions from a great big ensemble without ever sort of getting your hands dirty with the great big ensemble. Of course, it has this very strong weight sharing, which limits what it can do. but that's the kind of ensembles I'm going to use. And what I'm going to try and do is train a great big model, or a fairly big model, with dropout, and then show you that after it's trained, I can get the knowledge into a much smaller model. Later on, I'll do it with real ensembles, but for now, I'll do it with dropout. So I just said all that. If you have more than one hidden layer, you do the same thing. The math is no longer correct, but who cares? It's a very good approximation to what you'd get if you ran all these dropped-out models and then averaged. You can show that if you have to run about 100 times through this net before you start doing better than just taking the mean net, where you halve all the weights, and you don't end up doing that much better. So it's good enough for us. So here's an experiment on MNIST. If you take a vanilla backprop net of the current variety, which uses, it should use more layers, but I use 2 layers of 800 pin units, each of which was a rectified linear unit, and all that means is the output of the unit is the max of 0 and its total input. And its total input is just a linear filter on the units in the layer below, on the outputs of the units in the layer below. So, train a vanilla net with vanilla backprop, you get 146 test errors. And sometimes you get 140, sometimes you get 153, but that's a perfectly reasonable number. If you train a bigger net, so this has about twice as many parameters, and we're going to train it with dropout, and we're going to do other things. We're going to constrain the weights. We're going to say the weights coming into each hidden unit, the L2 norm of that weight vector mustn't exceed a certain size. That's much better than using standard L2 decay, because it means when some weights really want to get big, they put pressure on this L2 norm, and so the down pressure on all the other weights gets bigger. It's like a Lagrange multiplier, right? It exerts enough down pressure to keep the constraint where it is. And so it amounts to saying if some inputs want to have big weights, the amount of weight decay you have on other inputs gets bigger. And that does a very nice job of forcing other things to 0. That's all on the side. I also jitter the input. And everybody knows that transforming the inputs to a neural net in ways that don't change the label by translating them around, for example, is a big help. This is a non-convolutional net, and this wouldn't be so much help if it was convolutional. But that now does much better. That gets 67 errors. And that's about the state of the art for non-convolutional nets. You can do a little bit better, but that's a pretty good score. So the question is, if I now take this net, look at the predictions it makes on the different training cases, but look at the predictions it's making when I raise the temperature of the softmax to temperature, say, 10, some number like that, can I use those soft targets to transfer what this net learned into a net like this? And the real question is, what I didn't know is, will I get some score like sort of 130, saying, hey, I can make this net do better by using soft targets? Or will I get some score like 75, which says, hey, I can make this net do almost as well as this net? And will I be able to get some low score like 75 without using dropout or weight constraints or jittering? In other words, once this guy has learned and produced his soft targets, are they really, really rich information that's a much better thing to use for training than the original hard targets? And you can probably guess the answer. If you train that net that got 146 errors using the soft targets from the big net trained with dropout, it gets 74 errors. So it's almost as good as a big net. Almost all the benefit that we got from using dropout and jittering and all that stuff comes across the little net. Even though when you train the little net, you train it on the same training data without using dropout and without jittering the inputs. So it was very surprising to me that the benefit you get from transforming the inputs transfers across to the little net, even though you're not transforming the inputs. Transforming the inputs makes the big net generalize much better. And the way the big net is generalizing, information about how to generalize is what's showing up in this dark knowledge. The dark knowledge is telling you all about how you should be generalizing. It's telling you you shouldn't generalize from cow to car, because cow is 1,000 times more likely than car, even though one's 10 to the minus 6 and the other's 10 to the minus 9. If cow was 10 to the minus 6 and horse was 10 to the minus 7, it would be telling you maybe you should be generalizing from cows and horses. They're both very similar bets here. So there's lots of information about how to generalize in those soft targets, and none of that information is in the hard targets. Okay. So what the big net has really done, or the ensemble, if you take the soft targets, is it's learned a similarity metric. It's learned what's like what. And you're telling the net, the little net, what's like what. And that's making life much, much easier for it when it learns. You'd have thought by now at least the NIPS referees would have said, hey, there's something interesting here. But I'll tell you what the NIPS referees said. You never get over being pissed off at having papers rejected. The referees said, the net that you transfer the knowledge to does worse than the big net, so what's the point? Now the paper very carefully explains the point is A, this is an amazing effect, and B, it'll allow you to have very little production model. Oh well. So here's what things look like on that MNIST experiment. I'm afraid I didn't keep the actual digits. I should go back and do this again with the actual digits. So what we're seeing here is these are the 10 classes. Each row is a training case, and it's showing you the soft targets for a training case. So all of these ones are 2s. I chose just a patch that has a lot of 2s in. And if you look at this 2 here, it's very confident it's a 2. It thinks it might just be a 1. There's a small chance of a 1. And there's a very small chance of a 6, and nothing else. Whereas if you look at this 2, it says this 2, it could be a 0, or it could be a 3, or maybe a 7 or an 8. If you look at this 2, it says this might be a 4 or a 7. In other words, they're very different patterns of similarity of these different 2s. And I'll bet you if I showed you the 2s, you would see why. Why I regret not having kept them. That's the extra information you're giving them. So now the labels don't consist of saying it's a 2. They say, this is the kind of 2 that looks a bit like a 3 and a bit like an 8. And this is the kind of 2 that looks just like a 7. And that's why it's so much more helpful. So here's a really surprising result. I wanted something to sort of make people surprised by this, because it's a huge effect. So I said, what if, when we train the little model, we never show it a 3? So we train it just as before, but in the transfer training, the little model never ever gets to see a 3. As far as it's concerned, a 3 is this mythical object. It's as if you're learning about pictures and someone said, that's a Rubens. And it's a little bit like a Raphael. And they said, actually, it's a Rubens, and it's not at all like a Raphael. And then they said, this is a Leonardo, and that's a tiny bit like a Raphael. You've never seen a Raphael, but they tell you all these things. The question is, the first time you see a Raphael, will you say, oh, that must be a Raphael? Well, here we go. If you train it never having seen a 3, but on soft targets, after training, it gets about 90% of the 3s right. It's 88% of the 3s it's getting right. And the reason it only gets 88% of them right is because it's got a huge negative bias for 3. It's never actually seen a 3. So during training, because it's also trying to match hard targets, it's said 3s are extremely improbable things. They're like unicorns. They just don't occur. After training, what you do is you just take the bias of the 3 and you raise it. And because I was doing this research, I cheated in a way I wouldn't allow a student to get away with, which is I looked at the test set and said, what's the amount I raise the bias by to do best on the test set? But it's only one number, so it's only a little cheap. And if you do that, you get 98.6% of the 3s right. And notice that this is the same performance as this net got when it was trained in the normal way on all the data. In other words, train a big model to be very good with jitter and dropout, transfer its knowledge to a little model, but when you do the transfer, never show the little model only 3s, and the little model will be as good at 3s as if you trained it in the normal way on all the data. That's amazing, I think. Well, I think it. So I got carried away and said, well, what if I only show it 7s and 8s when I'm training it? So you're training it to recognize all 10 digits, but the only things you're ever going to show it are 7s and 8s. So you're only going to show it Rubens and Leonardos, and you say this is a Rubens is a bit like a tiny bit like a Titian, and here's a Leonardo that's not much like a Titian at all, and this one's a bit like a Caravaggio and all that. And in the end, you expect it to be able to recognize Titian and Caravaggio. It's never seen any of them. It sounds extremely implausible, right? Well, here's what happens. Obviously, I chose 7s and 8s judiciously as very different looking digits, but it looks kind of arbitrary because they're next to each other. That's the art of giving talks. If I'd chosen 6s and 0s, this wouldn't have worked. Well, it wouldn't have worked so well. After you've trained it just on 7s and 8s, it gets about 50% errors on all the digits, which is already pretty impressive. If you then lower the bias of 7 and 8, I lowered them by the same amount, so it's still only one number, but I chose that amount to optimize performance on the test set. So very naughty, but only one number. It now gets 87% correct on all the digits. So this is saying these soft targets are hugely informative. In fact, we have a conclusion to that effect. Everybody who does object recognition knows that transforming the inputs is a great thing to do. If you don't do that, you're not going to win any competitions, because you're giving so much more information when you affine transform them and distort them and change the lighting and all that stuff. But that's a very brute force method, and it means you've got a lot more data you have to train on. So it's a kind of brute force way of telling your neural net how it should generalize. Transforming the targets has a similarly large effect, and if you can get your soft targets from somewhere, it's much cheaper, because you don't have any more training examples. Each training example is now doing hugely more work for you. Whereas when you transform the inputs, you've got to wade through all these training examples. But of course you have to get the soft targets from somewhere. This idea has been tried by lots of people in one particular form, which is the idea we could get better targets for training a classifier by taking our object classes and making a tree. So I'm predicting Doberman, and in my tree that's under dog, which is under mammal, which is under animal, which is under living thing and whatever. And instead of just getting it to output a 1 for Doberman, I get it to sort of output the whole path to the root of the tree. I get to say all the things in that path should be lit up. Obviously that's giving me more information per training case, but obviously that's not nearly as good as having soft targets. I mean, it has the advantage you might be able to get that information without having to train anything, but you can't capture visual similarity in a tree. We're interested in visual similarity here. And the point is, some cows look like ostriches, just because of the trick of the lighting. And if the cow happens to look like an ostrich, you would like your net to be told this is a cow that looks a little bit like an ostrich. And that's not going to show up if you have this tree. I can't actually imagine a cow that looks like an ostrich, but I bet you could do it. You'd get a neural net to find it. Okay. So I'm going to give you some real results in a minute on production-size systems that get better when you do this trick. But before that, I want to show you the first experiment Oriol did, which was he started with a kind of production acoustic model. So this was the model that until quite recently was used in the cloud by Android phones. They would take filter bank representations of what you're saying every 10 milliseconds. Well, there's a heavily engineered implementation of this, of course. And they would put those through an acoustic model to predict 14,000 possible HMM states. And these are states of triphones. And this was a neural model with 8 hidden layers of rectified linear units. And so Oriol took that model and took a trained model and said, what happens if I take that trained model and I get it to give me soft targets now? I look at the outputs of the model at a higher temperature, and I then train a new model with those soft targets and the hard targets too, but downweighting the hard targets. But I'm going to train the new model on only 3% of the data. And you do that because you want to see how much information is in these soft targets. Well, if you take just 3% of the training data and you train the original model, it gets to 44% correct, frame classification, and then it starts getting worse again. You have to stop it because it then goes down quite sharply. It's seriously overfitting. If you do it with soft targets coming from the big model that was already trained, but you're still only training on 3% of the data. The transfer set is just 3%. With these soft targets, it goes up to be almost as good as the trained model that gave you the soft targets, and then just stays there. It doesn't get worse again. Soft targets are very, very good at not letting you overfit. We'll come back to that. So soft targets really are a very good regularizer. Okay, so here's a real result. This is the kind of thing Google might be interested in. You take 10 models and you train them separately, and on average they do that. 58.9% correct. This is the production acoustic speech model of Oriol Saga. Actually 2 years ago. If you average those 10 models, you get 61.1% correct. This improvement does go through to the word error rate. It gets a bit smaller at the word error rate, but you do get a better word error rate too with the ensemble. And the question is, if we now say, yeah, but we don't want to run 10 models, we just want to run one model the same size as these models, what happens if we go back and now we take one model this size and we train it with the soft targets from the ensemble that got that? And the answer is you get 60.8% correct. And you're getting 6/7 of the win that you get in the ensemble. The gap from there to there, this is 6/7 of the way to there. So Google now, for the same price, you could run this model or this model, for the same cost, and you'd obviously be better off running this model, if it went through to word error rate. In word error rate, the word error rate of this model is 10.9, and this one is 10.7, and this one's 10.7. I want to say a bit about the prior work by Rich Caruana, because he obviously had this basic idea a long time ago, and he showed that it worked and people just ignored it. He did it in a slightly different way. What he would do is take the ensemble, compute the average logits from the ensemble, and then he'd do regression on those logits. So he'd try and make his new model produce the right logits by just measuring the error in the log domain and just doing linear regression. So he's using half the squared difference between the logits. And the question is, how does that relate to taking the softmax and raising the temperature? And one thing that intrigued me was, as you raise the temperature, the distribution gets softer and softer, and so your cross-entropy gradients get smaller and smaller. You're going more and more towards a uniform distribution. But suppose you went almost to the uniform distribution, but increased the gradients. So what you're going to do is you're going to scale up the temperature, but you're also going to scale up the learning rate. Will that look like matching the logits? And the answer is yes, it does. So here's a lemma. If you take e to the epsilon, the gradient of e to the x is e to the x. So when epsilon is 0, the gradient of e to the 0 is 1. And because the gradient of e to the 0 is 1, that means e to the epsilon is 1 plus epsilon. Okay. So now what have we got here? We've got, this is the cross-entropy cost function, and this is the derivative of the cross-entropy with the soft target with respect to the logit for one class I. So Zi is the logit in the model that you're learning, the distilled model. I put a t over this side so it doesn't clutter things up. If t's 1, you don't normally see it. And this derivative is just the difference between the probability that the model you're learning assigns to that class and the soft target probability of that class. That's the familiar gradient for logits. And if you look, what is this probability? What is pi? Pi is e to the zi divided by the sum of all e to the zij's, but with this temperature in there. We're scaling it by the temperature. So these are the logits of the model that we're learning. These are the logits of the model that was already learned, the big ensemble or the big model trained with dropout, that are used to derive the soft targets. So these are the logits that are used to compute this TI. And so now using this fact, you can simplify this thing to be this. This is 1 plus zi over t. And you can simplify this thing to be this. The bottom line you can simplify every term in the same way, and there's going to be n terms if there's n classes. So there'll be n ones, which we can take outside, and there will be n different terms, one for every j, of this form. Now suppose that on every single training case, what we do is we take the logits and subtract off their mean from all the logits. With a software, subtracting the mean doesn't make any difference. Okay, it just drops out in the equation, it's irrelevant. It's the sort of surplus degree of freedom in the softmax. But if we do subtract off the means, and so we say these are the zero mean logits, then the sum of all those guys is 0, because the sum of all the VJs is 0. And the sum of all these guys is 0, so these things are both n. So we can take out that n and we can stick it here. We can take this t, we can stick it there. These ones cancel each other out, and you get zi minus vi, and 1 over nt times that. And then if we remember this t over here and take this across, you get 1 over nt squared times this. And if you think about it, if your cost function was the difference of the logit of the distilled model and the model whose soft targets is like this, this is just the regression. So in the limit, as the temperature goes to infinity, this is the same as what Rich Caruana was doing, provided, of course, you scale the learning rate by 1 over nt squared. You have to have an infinite learning rate because you've got infinitesimal gradients when you use this infinite temperature. But Rich Caruana's thing is just the infinite temperature limit. And what I discovered using various temperatures is high temperatures. To begin with, I discovered the sort of optimal temperatures, like 20 or 30. But that depends very much on your learning rate. And if you scale your learning rate like this, then it turns out all high temperatures work pretty much the same. So the technique that Rich Caruana is using is very like this thing at high temperature. If you have a model that's too small, if your distilled model is too small to capture all the knowledge in the big model, then it's best to use a lower temperature. Because at high temperature, you're saying modeling big negative logits is as important as modeling big positive ones. And if you can't capture all the knowledge, you'd rather capture the knowledge in the big positive logits. So using a lower temperature works better. People at Microsoft recently produced a speech paper, influenced by Rich Caruana, in which they just use the cross entropy, so they're using a temperature of 1. So Microsoft has claimed 1 and infinity, and Google claims all the other numbers. Here's an interesting little experiment. This is to appeal to psychologists. Suppose instead of training one ensemble and then trying to transfer it, what we do is we have a whole ensemble of nets, and as they're training, they're all looking at what the other guys are up to. So we initialize them with different weights, and we store with the data, we have mini batches of data, and with each mini batch of data, we store the logits that came from the other models when they looked at that mini batch, and we get the models to go through the mini batches in different random orders. So I'm a model, I come to a new mini batch, and with that mini batch is stored my old predictions and everybody else's predictions. I average them all. It's a slightly out of date prediction produced by all the models. And when I take the geometric mean, I'll get, and then raise the temperature on it, I'll get soft targets. And so I can use those soft targets in addition to the hard target. So I'm using everybody else to help regularize me. And now you don't have to first train an ensemble and then transfer it. You can be using all the other guys as the ensemble as they're all training. And it works very nicely, at least on MNIST, where there's a major regularization problem. So if you train individual models, they get 158 test errors. If you ensemble them, you get down to 143 errors. So if you take soft target from this ensemble, you'd expect your little model to do your one model that's trying to capture the knowledge, to get about 145 errors or something. But if you actually do this ensembling as you're training, you let everybody look at what everybody else is saying as you're training, you actually do a lot better. The individual nets, on average, get 126 errors, and the ensemble of them gets 120 errors. So the ensemble win has gone down because, of course, they've all been looking at what the other guys are saying. And so when you ensemble them, they've got much more in common than independently trained nets. But they're all much better, and they're all much better than this whole ensemble was. This is a nice model for a scientific community. What you ought to be doing is looking at the real data, those are the hard targets, but also looking at what everybody else is saying. Pay a small amount of attention to that, and pay some attention to the hard targets. And it doesn't matter if your model of what everybody else is saying is a little bit out of date. Like it's what people were saying 6 months ago, that's fine. That'll help. You shouldn't just look at the data, you should look at what other people are saying. Okay, that's what this says. The last thing I want to talk about is how to try and make big ensembles mine data more efficiently. Because there's some problems Google has where you can't afford to train a big ensemble. It took them 6 months to train one model, and they don't want to go back and train a dozen models. 6 months to train one model on lots of machines. So I'll start by talking about ImageNet. I'm not going to show you the results on ImageNet because we haven't got that working nicely yet. I'll show you results on something else. But on ImageNet, for example, you could have a specialist model that specializes in discriminating different kinds of mushrooms. This specialist model does look at other things as well, but what it really knows about is how to discriminate mushrooms. In fact, it's going to know about how to discriminate between mushrooms. It's also going to learn how to tell whether something's a mushroom or not. We can decide on these subsets that the model is going to specialize in by training one general model, and then getting it to produce soft targets, and then doing k-means clustering on these soft target vectors. That'll tell you sort of natural classes of computable things. And in fact, if you do that, mushrooms comes out as one of the classes. All and only the mushrooms come out in this k-means cluster. Cars come out as another cluster. In fact, there's several clusters for cars. So the idea is you would first train one generalist model. You'd then use its softmax at high temperature so you can see all its side bets. You would do k-means clustering on those vectors, and now you would get your data divided into a bunch of subsets. And we actually did a bunch of different k-means clustering, so we had overlapping subsets. So each data point occurred in many subsets. And the idea is you're going to train a specialist now to be very good at dealing with a subset. And then the long-range idea is you're going to combine these specialists into one model, and now you're going to be able to train these specialists all in parallel, combine them into one model, and now have one small model that's really good. You see, if you're training on 15,000 classes, and you're training the normal way, what happens is you see one kind of mushroom, and then 10,000 training examples later, after you've changed the weights quite a lot, you see another kind of mushroom that's awfully similar, and there's a very subtle difference in their gills that'll tell you which is which. But this is 10,000 examples later, and you need to get your filter good for detecting that subtle difference. And the only way you're ever going to do that is by using a tiny learning rate, so you haven't yet forgotten this thing 10,000 examples ago, and you can contrast it with this thing now. And that's why these big models go very slowly at the end. They could go much faster if you could somehow have the examples that you need to compare, have the data enriched in those, so you can just focus on those and getting the filters right for those. So the problem with specialists is, because they're focusing on a much smaller subset, they're going to overfit. And this is why mixtures of experts is it's a lovely academic idea, that's, as far as I know, not really used in practice. The problem with mixtures of experts is the experts will overfit, even on huge data sets. So, here's one way to prevent specialists overfitting, and I no longer think it's the best way, but it works. You train a generalist model. The generalist model has all the low-level vision stuff, all the convolution filters, and you initialize your specialist to that generalist model, and then you train it to distinguish mushrooms from non-mushrooms, and also to distinguish between mushrooms, and you don't train it for very long. So we're just going to use early stopping. We're going to say we take this generalist model, and now we're going to move it in lots of different directions to accommodate all these fine distinctions, and then we're going to average all those and see what happens. After you've trained a specialist model, obviously, when it gives you the probability of mushroom versus non-mushroom, it's going to grossly overweight mushrooms because we've enriched its training data, so 50% of the things it sees are mushrooms. Whereas in fact in the true data set, maybe 1% of mushrooms. Well, you can correct that. You just take log 50 and you add it to the log digit of the mushroom of the dustbin class of mushrooms. And that just corrects the softmax, so non-mushrooms now get much more likely. So that's one way in which you can do this. And we did it on the Geoff, Dean and Oriol did it on the GFT dataset. This is an internal Google dataset. Greatly annoyed the referee. It's problematic, right? You want to show that you can have a method that works on big data, and the referees complain we should have used smaller data set. So it's got 15,000 different classes. It's got 100 million images. They trained a large convolutional neural net for 6 months, and it gets 25 correct top one. Of course, they were training it not to publish, but in order to get good results. So the training goes like this. You train it for a couple of weeks, and then someone says, hey, what did you set that learning rate to? Or what did you set the momentum to? And the guy says 0.7. I think 0.9 would do better, so you change that and you carry on training. And so by the time you've trained this after 6 months, it's a kind of sociological history of beliefs about neural networks went into this training. And you don't want to train another one just the same. And you certainly don't want to start again. So what you'd really like to do is take this thing that you've trained and make it work better. So the idea was, we'll take this thing as our generalist network, and we'll make a copy of it, and we'll train this copy mainly on mushrooms, and not for very long, or mainly on something else. And we'll see if this slightly perturbed network really works better. And the answer is, it really does work better. It gets about 27% correct, and that's a big win compared to that. They wouldn't expect to be able. They would expect to go for another 6 months to get that to 27. And this only took a week or two. So Geoff, Dean, and Oriol actually trained 60 specialist networks. What they did was they did k-means clustering. They got 60 different clusters, but they used overlapping clusters, and they trained on those 60. And then they looked at test cases. And for a test case, what they did was they took the generalist model and they said, if the generalist model thinks it's probably in the class in which this specialist specializes, we'll run this specialist. So you don't have to run all the specialists. You're doing sort of triage with the generalist model, and then the specialist being used to refine within the class. So if the general model gets the wrong class altogether, you're not going to recover. At least not with this method. But typically, most of the errors are the general model gets it right. It gets that it's a mushroom, it just gets the wrong kind of mushroom. And then it would invoke the mushroom specialist, and the hope is the mushroom specialist will be able to give it advice, no, it's not one of those, it's one of these. So, if you look at the test cases, there's a lot of test cases where none of the specialists applied, and then there's a lot of test cases where one specialist applied, a few test cases where 9 different specialists applied. In other words, the generalist model's beliefs were such that you thought all 9 specialists might be relevant. And if you look what happens, this is the relative improvement of accuracy by combining the generalist model with specialists. The more specialists that apply, the better you do, more or less. And this is quite a big improvement in relative accuracy. And even around here, when you've got just 2 specialists applying, you're getting a 7% improvement in the relative accuracy. So this strongly suggests that you can quickly improve a big model by initializing copies of it and then training them very briefly on highly enriched data, so they're good at the fine distinctions. This ought to work for things like phonemes. They cluster nicely, so that the same kind of techniques might well work there. I think, retrospectively, there's something better we could have done. Combining models with dustbin classes isn't straightforward. And that's because a dustbin class isn't saying, I think everything in my class is equiprobable. It's telling you a constraint on the sum of those probabilities. But now when I have to combine a bunch of models, this model has a constraint on this sum of probabilities, this model has a constraint on that sum of probabilities. How do I combine them all? And you don't want to use the maximum entropy method, because max enter is equivalent to saying the model thinks the probabilities are all equally likely, and it doesn't. So what we do is we actually, just to combine specialists, I give you a test case, you have to combine the opinions of the specialists. That's an iterative process, but it's a very fast iterative process. And it works like this. Let's suppose we're trying to iteratively compute some logits to make our prediction. So these are the logits we're going to use to make the ensemble prediction from all these specialists. And we're going to be iteratively revising these. This is one of the specialists, and one of the specialists says, I give you the probability of these 3 mushrooms, and I give you the probability it's not a mushroom, and now you have to make use of this. So what you do is you minimize the cross-entropy between, here's a term, here's a term, here's a term, and here's one more term, the sum of these 3 and that. And because you're taking the sum of these 2, this specialist doesn't care how the information is distributed there. And it turns out it amounts to a version of the EM algorithm. It amounts to saying you're going to use your current beliefs about these to infer the relative probability of these. And it all works fine. I'm not going to explain the details of that because it's tricky and I'm not sure we need to do it anymore. So I think the right way to use soft targets and specialists is this. You train a generalist model, and then you use specialists that output all of the classes, but half the time you get them to use just the hard targets on their specialist class. So half the time the mushroom guy is looking at mushrooms and he's trying to say, how do I optimize all my parameters so I can discriminate these mushrooms? The other half of the time he's looking at things other than mushrooms and he's saying, how do I fit in with what the generalist believes about these other things? And that's a very good way of holding the knowledge where it is. You saw that in speech where just 3% of the examples were enough to prevent you overfitting. So here, 50% of its time is getting examples that are preventing it from overfitting. And then 50% of its time is able to focus in on fine distinctions of mushrooms. And we're about to start running this, and so obviously the thing I most believe in is the thing we haven't done yet. It's always like that. And I think this is probably the right way to use specialists. So just to conclude. We have a very clear conclusion, which is don't worry about how big your model is when you're trying to get knowledge out of data. Have a phase when you just get the knowledge out of the data into a model. Obviously you want it in a real model, something with parameters, not just the kind of thing we do in Berkeley. And you get it into a model. Then once you've got your model, it can give you soft targets. And now you've got your soft targets, it's very easy to train a small model. So that I think is solid. Caruana pointed that out a long time ago. Everybody ignored him. And everybody should pay attention to Caruana's 2006 paper, of which he wasn't the first author. You can find it easy. It's called Model Compression. That was a great paper that's been completely ignored by the machine learning community, which puts it in the same category as neural nets were for a long time. And then there's the speculation that for really big data sets, you should train one generalist model and then train lots and lots of specialist models, but regularize them by fitting the soft targets in the generalist model. And I think that may allow us to get very good on much, much bigger data sets quite efficiently. I'm done.